It's 1985, and a Freightliner with a screaming Detroit diesel 8V92 pulls into a truck stop with steam pouring from under the hood. The driver pops the engine cover to reveal cracked cylinder liners, blown head gaskets, and coolant mixed with oil. This wasn't a freak accident. This was the 8V92's Achilles heel that would ultimately kill one of America's most powerful engines. Today, I'm going to reveal why the Detroit diesel 8V92, despite producing over 500 horsepower and dominating highways for decades, represented one of the biggest strategic miscalculations in diesel engine history. The Detroit diesel 8V92 wasn't killed by emissions regulations or fuel economy concerns like most people think. It was killed by heat, specifically its inability to manage the tremendous thermal loads created by its revolutionary two-stroke design. To understand why this engine became too hot for its own good, we need to examine the very innovation that made it powerful in the first place. The 8V92 used wet sleeve cylinder liners, a design that seemed brilliant on paper but proved catastrophic in real-world applications. Unlike conventional engines where cylinders are bored directly into the block, the 8V92's cylinders were separate steel sleeves that slipped into the cast iron block and sealed directly against the coolant passages. This wet sleeve design allowed for easy rebuilds and theoretically better heat transfer, but it created a thermal nightmare that would plague the engine throughout its production life. Here's where the physics worked against Detroit diesel. The 8V92's two-stroke cycle meant it fired twice as often as a four-stroke engine, generating nearly double the heat per minute. Each cylinder produced approximately 62.5 horsepower at rated output, creating intense thermal stress on those wet sleeves. The temperature differential between the combustion chamber and the coolant could exceed several hundred degrees Fahrenheit during normal operation. The wet sleeves expanded and contracted with these extreme temperature cycles, but they didn't expand uniformly. The top of the sleeve closest to the combustion chamber expanded more than the bottom. This differential expansion created stress concentrations that led to cracking, particularly around the firing area where combustion pressures were highest. When these cracks developed, combustion gases would leak into the cooling system, creating a cascade of failures. But the real killer was cavitation. The violent pressure pulses from the two-stroke combustion cycle created cavitation bubbles in the coolant around the wet sleeves. These bubbles would collapse with tremendous force, literally eating away at the sleeve material through a process called cavitation erosion. Over time, this erosion would create pinholes and cracks that allowed coolant to enter the combustion chamber and oil to contaminate the cooling system. Detroit diesel engineers knew about this problem from the beginning. Internal documents from the 1960s show they experimented with different sleeve materials, coatings, and coolant additives to combat cavitation. They developed special coolant conditioners containing nitrites and molybdates designed to form protective films on the sleeve surfaces. But these solutions required perfect maintenance, something that proved impossible in real-world applications. The cooling system itself became a maintenance nightmare. The 8V92 required a 50-50 mixture of ethylene glycol and water with supplemental coolant additives. Coolant condition needed to be monitored regularly, and system flushes were recommended at intervals specified by Detroit Diesel or based on operating conditions. Miss these intervals and cavitation would destroy the wet sleeves within months. Fleet operators quickly learned that the 8V92's cooling system was unforgiving. A single overheating incident could crack multiple cylinder sleeves, requiring a complete engine rebuild. Unlike four-stroke engines that might survive occasional cooling system neglect, the 8V92 would catastrophically fail, often taking the entire engine with it. The Detroit Diesel 8V92 was engineered for perfection in a world that operated on compromise. While Detroit Diesel's marketing materials promised 500,000-mile service intervals and bulletproof reliability, the reality was an engine that demanded near-perfect maintenance in an industry where good enough was often the standard. The maintenance schedule for an 8V92 read like a laboratory protocol. Oil changes were required every 15,000 miles with specific oil. The air cleaner needed service every 25,000 miles. Fuel filters required changing every 30,000 miles. The injectors needed adjustment every 100,000 miles. Most critically, the cooling system demanded constant attention with coolant testing every 25,000 miles and complete system flushes every 100,000 miles. But here's what killed the 8V92 in practice. These weren't suggestions, they were requirements. Miss an oil change interval on a Caterpillar 3406 and you might get away with it. Miss one on an 8V92 and you could destroy the engine. The two-stroke design created contamination levels that four-stroke engines never experienced. Combustion byproducts would accumulate in the oil at twice the rate. And the wet sleeve design meant any cooling system contamination would immediately affect engine lubrication. The unit injector system, while mechanically elegant, required specialized knowledge that many mechanics simply didn't possess. Each injector had to be timed to within 1 degree of crankshaft rotation. The fuel racks had to be synchronized across all 8 cylinders. The governor linkage required precise adjustment to prevent engine runaway, a condition where the two-stroke engine would literally destroy itself by over-revving. Fleet maintenance managers quickly discovered that the 8V92 couldn't be serviced by just any mechanic. It required Detroit diesel-trained technicians who understood the intricacies of two-stroke operation. This created a bottleneck in service availability and drove up maintenance costs significantly compared to competitors. The parts cost told the real story. A complete set of wet sleeves for an 8V92 cost over $3,000 in 1980s dollars, equivalent to nearly $10,000 today. A single unit injector cost $400, and you needed 8 of them. Compare this to a Cummins Big Cam, where a complete in-frame overhaul could be done for less than the cost of just replacing the 8V92's cylinder sleeves. Marine applications reveal the 8V92's maintenance demands most clearly. Saltwater environments accelerated corrosion in the cooling system, making the already critical coolant maintenance even more demanding. Commercial fishing boats and tugboats that operated around the clock couldn't afford the downtime required for the 8V92's maintenance schedule. Many operators switched to Caterpillar 3408 or Cummins KTA engines specifically because they could tolerate neglect better than the temperamental Detroit diesel. The final nail in the maintenance coffin was parts availability in remote locations. While Detroit diesel had an extensive dealer network, the 8V92's unique components meant that a breakdown in rural areas could strand a truck for days waiting for specialized parts. Competitors like Caterpillar and Cummins had achieved much better parts commonality across their engine lines, making roadside repairs more feasible. Detroit Diesel's decision to pursue the 8V92 design represented one of the biggest strategic miscalculations in diesel engine history. While their engineers were perfecting a 500 horsepower screaming machine, their competitors were quietly developing engines that prioritize durability, fuel economy, and ease of maintenance, the qualities that actually mattered to truck operators. The numbers illustrate Detroit Diesel's relentless pursuit of power. The 8V92, with its 736 cubic inches of displacement, could produce up to 500 horsepower and 1,400 pound-foot of torque in its most advanced turbocharged and after-cooled configurations, an impressive 0.68 horsepower per cubic inch. However, during the 1970s, most 8V92 engines used in highway trucks typically produced between 350 and 435 horsepower, with the higher outputs arriving in later years as technology advanced. Detroit Diesel's marketing department capitalized on these headline figures, positioning the 8V92 as the ultimate power plant for serious truckers. But while Detroit was chasing horsepower numbers, Cummins was developing the Big Cam series with a completely different philosophy. The big cam, introduced in 1976, produced 400 horsepower from 855 cubic inches. Less power per cubic inch than the 8V92, but with dramatically better fuel economy and reliability. More importantly, the big cam could run 500,000 miles between overhauls with routine maintenance, while the 8V92 was lucky to reach 300,000 miles before requiring major work. Caterpillar took an even more conservative approach with their 3406 series. The 3406A produced just 350 horsepower, but it was virtually indestructible. Fleet operators discovered they could run 3406 engines with minimal maintenance and still achieve 750,000-mile service lives. The engine was so robust that many operators simply changed the oil and filters and ignored everything else until something actually broke. Detroit Diesel's engineers weren't blind to these competitive advantages. Internal company documents from the late 1970s show they understood the 8V92's limitations. They knew the wet sleeve design was problematic. They knew the two-stroke cycle created maintenance challenges. They knew the cooling system was fragile, but they had invested too heavily in the technology to change course. The company's response was to double down on performance. They developed turbocharged versions that pushed power output even higher. Specialized versions for marine and industrial applications exceeded 600 horsepower. Each increase in power made the thermal management problems worse, but Detroit Diesel continued to believe that raw performance would overcome practical concerns. This strategy might have worked in the 1960s when truckers were willing to accept high maintenance costs for superior performance. But by the 1980s, the trucking industry had changed. Deregulation had created intense price competition, forcing operators to focus on total operating costs rather than just initial performance. Fuel economy became critical as diesel prices rose. Reliability became essential as just-in-time delivery schedules left no room for breakdowns. Detroit Diesel's competitors understood this shift and adapted accordingly. Cummins developed the L10 engine specifically for fuel economy, achieving 6.5 miles per gallon in over-the-road applications. Caterpillar focused on durability, with some 3406 engines accumulating over 1 million miles without major repairs. Both companies invested heavily in electronic controls and fuel injection systems that improved both performance and efficiency. Meanwhile, Detroit Diesel remained committed to mechanical fuel injection and the fundamental two-stroke architecture. They made incremental improvements: better materials, improved cooling system designs, electronic governors, but never addressed the core issues that made the 8V92 impractical for most applications. By the mid-1980s, the Detroit Diesel 8V92 found itself fighting a war on multiple fronts, and it was losing every battle. The engine that had once dominated American highways was being squeezed out by regulatory changes, market demands, and technological advances that its fundamental design simply couldn't accommodate. The first major blow came from fuel economy regulations. The 1975 Energy Policy and Conservation Act didn't directly regulate truck fuel economy, but it created pressure throughout the transportation industry to improve efficiency. Fleet operators, facing rising diesel prices and increased competition, began demanding engines that could achieve better than 5 miles per gallon in over-the-road service.
To reduce our use of foreign petroleum by raising import fees on each barrel of crude oil by $1 on February 1st, another $1 on March 1st, and a third on April 1st.
The 8V92's two-stroke design made this impossible. The scavenging process that gave the engine its power also wasted fuel. Fresh fuel charge would escape through the exhaust ports during the overlap period when both intake ports and exhaust valves were open. This phenomenon, called short-circuiting, meant the 8V92 consumed approximately 15 to 20% more fuel than equivalent four-stroke engines under identical operating conditions. Detroit Diesel engineers tried various solutions to improve fuel economy. They developed better port timing, improved fuel injection systems, and even experimented with variable geometry turbochargers. but the fundamental physics of two-stroke operation limited how much improvement was possible. The emissions regulations that began in earnest with the 1988 model year created an even bigger problem. The 8V92's two-stroke cycle made it nearly impossible to control nitrogen oxide emissions. The high combustion temperatures necessary for power production created excessive NOx, while the scavenging process made it difficult to implement exhaust gas recirculation or other emission control strategies. Detroit Diesel spent millions trying to make the 8V92 emissions compliant. They developed new combustion chamber designs, improved fuel injection timing, and even experimented with catalytic reduction systems. But each attempt to reduce emissions hurt performance or reliability. The emissions-compliant versions of the 8V92 produced less power, consumed more fuel, and required even more maintenance than the original design. The final regulatory blow came from noise regulations. The 8V92's distinctive scream, while beloved by truckers, exceeded noise limits being implemented by cities and states across the country. The engine's high-frequency exhaust note was particularly problematic, as it carried much farther than the lower-frequency rumble of four-stroke engines. Attempts to quiet the 8V92 proved futile. The noise was inherent to the two-stroke design and couldn't be eliminated without fundamentally changing the engine's character. Muffler systems that reduced the noise to acceptable levels also restricted exhaust flow, reducing power and increasing fuel consumption. Market demands were shifting in ways that played to the 8V92's weaknesses. The trucking industry was consolidating into larger fleets that prioritized total cost of ownership over raw performance. These fleet operators had sophisticated maintenance tracking systems that clearly showed the 8V92's higher operating costs. They could quantify the additional downtime, the higher parts costs, and the specialized labor requirements. Owner-operators who had been the 8V92's core market were being squeezed out by deregulation and economic pressures. The independent truckers who appreciated the engine's power and character were being replaced by fleet drivers who simply wanted reliable transportation. The emotional connection between driver and engine that had sustained the 8V92's popularity was disappearing. The death of the Detroit Diesel 8V92 wasn't a sudden event. It was a slow strangulation that took place over nearly a decade. By 1995, production had essentially ended for on-highway applications, though specialized versions continued for marine and industrial use until the early 2000s. The engine that had once powered America's highways had become a relic, killed not by any single factor but by the accumulated weight of its fundamental design limitations. The wet sleeve cooling system that had seemed so innovative in the 1960s proved to be the 8V92's fatal flaw. Despite decades of improvements, better materials, improved coolant formulations, enhanced maintenance procedures, Detroit Diesel never solved the basic problem of cavitation erosion and thermal stress cracking. Fleet operators learned to budget for sleeve replacement every 200,000 to 300,000 miles, making the 8V92's total cost of ownership uncompetitive with four-stroke alternatives. The maintenance demands that had been acceptable when labor was cheap and trucks were simpler became impossible to justify as the industry evolved. The 8V92's requirement for specialized knowledge and perfect maintenance made it unsuitable for an industry moving towards standardization and cost reduction. Detroit Diesel's strategic focus on power over practicality proved to be a miscalculation of historic proportions. While they worked on power, their competitors were developing engines that better matched market needs. The Cummins N14, introduced in 1988, produced comparable power with better fuel economy, lower emissions, and dramatically reduced maintenance requirements. The Caterpillar 3406E offered similar advantages with even better durability. The regulatory environment that emerged in the 1990s was specifically hostile to two-stroke engines. Emission standards, noise regulations, and fuel economy pressures all favored four-stroke designs. Detroit Diesel's attempts to adapt the 8V92 to these new requirements resulted in engines that retained all the original weaknesses while losing much of its performance advantage. Perhaps most tellingly, Detroit Diesel itself abandoned the two-stroke philosophy. The company's Series 60 engine, introduced in 1987, was a conventional four-stroke design that directly competed with Cummins and Caterpillar. The Series 60 became one of the most successful diesel engines in history, proving that Detroit Diesel could build reliable, efficient engines when they abandoned the two-stroke architecture. Today, the 8V92 exists primarily in the memories of truckers who remember its distinctive scream and in the specialized applications where its unique characteristics still provide value. Marine operators still use 8V92s in applications where high power density matters more than fuel economy. Stationary power generation facilities appreciate the engine's ability to start quickly and reach full power immediately. The 8V92's legacy isn't entirely negative. The engine pushed the boundaries of diesel performance and proved that American manufacturers could build engines that competed with anyone in the world.